Thank you for coming to our 12 o'clock session. This is a data storage and IO related session. The first talk we have is from Scott Klasky from Oak Ridge Lab. Second talk will be a video presentation from Shadi Ibrahim from INRIA in France. He'll be online for Q&A though afterwards, but Scott has a very long talk, so we're going to try to give him pretty much the entirety of the 30 minutes, and he has said, please sit with him at lunch and talk things over so that way he can get more information out and we can still have a good Q&A. So with that, I will have Scott get going here.
Thank you, Jay. And again, this is roughly a 12-hour presentation, which I gave in Australia, condensed to less than 30 minutes. So what that means is I can't go over specific details, but please ask me. It's very easy to Google me. So again, I want to really thank everyone for inviting me to come here. There's a lot that I can talk about, but one of the most important things I'll say is everything I present is basically resting on the shoulders of others. Jay was one of my, okay, this is going crazy. Jay was one of my students. I've had so many people that have come and worked with me on what I'm about to present. So this is sort of my history since grad school. I have an earlier history before that from Cray 1s and IBM 3090s. But one of the things I just want to point out to you, where yes, I come from the place where we have frontier. I'm viewed as the person we'll call on the bleeding edge of Oak Ridge. But I think about the applications. And through all these years, when I was a student in general relativity, going from, in the 90s or late 80s, we had a gigaflop processor. And yet I know people think SSDs are modern, but we had those on our Cray. And we had a really good ratio of compute to storage bandwidth. But then as we've gotten massively parallel, as we've changed, this ratio has gotten so much worse. And what that means is that we have to do a few things. We have to really be smart about how we do IO to, say, storage, to and from. We have to be really smart about how we move data from instruments over to compute, from this edge to HPC. We have to be really smart about what do we do, what we'll call in situ, staging, or whatever you want to call it, to have these advanced workflows. And then now we have to be even smarter. Okay, we have to be able to reduce the data. So these are all the techniques. And what we advocate is what I really found profound from what Amazon did was we basically said, we're going to have a service-oriented architecture. And what that meant was we're going to have a unified interface where every single service in Amazon is going to then have this public interface so that you can publish and subscribe. A long time ago, again, when Jay was much younger, I was about the same. And what we had was a way to say, how do we do this for what we call the exascale age? So this was when we were just getting to a petaflop computer, and we said, we have to think about the exascale and the transformation. How do we have ways to do this so an application can just think about going to storage, but then you can say, well, instead of that, create an advanced workflow, don't change anything, and go in memory. Hey, have a remote instrument doing the same thing. Have this go very efficient. So about our way was to say, how do we actually implement this vision? So in this, what we said is a unified interface. How do we create something? In this case, we did Adios, where it's the adaptable IO system, where it just publishes, subscribes. But we have to do it very efficient. And what you'll see here on the table is we have a much larger table, but again, due to space here, I'm just going to say we have so many applications where they can go to storage in over 1 terabyte per second. Like SpecFEM 3D, it's a code used around the world for global tomography. They get 2 terabytes per second. So the codes that I see, we are generating petabytes of data today. And as we're moving the frontier, we're getting to hundreds of petabytes. So we need a way to say, how do I have this componentized? How do we have this abstraction? So then I can switch from files over to then in memory or over the wide area network or local area network, and just do it in a way so that users don't program. They don't think about how it's being done. They don't think about all the parallelism. But what we do is we put the proper, in these cases, they're engines, the little things orbiting around Adios. I know you can't read the text there, but they're just engines. And then we have a way so that different collaborators, so if we have a collaborator in the UK, they can help create an engine which talks directly to NVMe so that we can even avoid the file system to go faster. So we have collaborators who can just independently develop these along the way to be very high performance. Everything is open source. Everything, we welcome contributors. And again, we want to put your name on there. And because there's so much diversity, we really think that the great ideas come when we come together for this. So why do you use it? When we talk scalable performance, we have to think scales are data sizes. You see petabytes going to exabytes. We see the number of processes that people run on, or the number of variables that people work on, or the number of steps, like a time step or other forms of steps. It's also, you can just run with this and things just work. This is why the SKA in Australia came to me a long time ago. It just works. So what we want to be able to do is do very advanced things. This is just a case study. I take this because we had this paper, and for all cases, being I'm an ex-physicist, sometimes I'm always talking to the lead physicist. WarpX, they just won in supercomputing the Gordon Bell Prize. They have an adaptive mesh refinement code. And one of the things that you'll see in the upper left, I guess there's no way to point, but basically, if you go in the upper left, this is in terms of writing performance, and we have a log scale. So from their previous implementations, when you actually look at what was in orange, that was what they were doing. And you can see this is a world of difference in performance. I hope you can see that when we talk about factors of 100 higher performance than what they thought was the state of the art. That makes a huge difference in the time. But what was more important and what was this paper was, but for reading performance, when you rethink of I/O, instead of doing what we'll call logic contiguous, which is again just making the data look on disk like it was written from one process, if you think about the parallelism, because you have parallel storage systems, you can lay things out in such a way so that when you read back from more than one process, so think everything today has multiple cores. So what I circled in yellow was all about what was one node. This was done on the Summit supercomputer, or old stuff at Oak Ridge. Still pretty fast. But what you'll start to see is that for all the types of ways to access data, whether it's taking a 2D slice this way in the room, or this way, or the other way, or you're looking at some sub-volume, you can really increase the performance when you read. So we can have orders of magnitude in performance for writing and reading the storage. Or in this case, I'm also one of the creators of what we call one of the ECP exascale computing project applications. This is Fusion, and we're coupling two codes. I won't go into that. Besides that, we have a mathematical coupler. We talk directly with Adios, and we see that in the coupling, we take less than 1/10 of the time, 0.1% of the time spent in all the coupling. So it's speed, performance, scalability. And when we think about all the ways then we can couple, we can have things where we can go directly with memory referencing, where one application just stops, the other comes in. Or we can do things which we can deal with files going to storage, or we can go over the network. And then there's different backbones from MPI to lower level from RDMA, different implementations of that. MPI underneath Adios for doing in memory. There's no one solution, and that's the point here. Wide area network. We had demonstrations years ago. We were running something in Singapore, and we were in the we were in the supercomputing showroom floor, and we were just doing in situ viz from, I forget where it was at the time, maybe Dallas. But the point is, we can do all these options, and we need to have the options. So the other thing you've heard in all the keynotes is this convergence of HPC with AI. What that does is it creates a lot of variability, and that's what some of these effects that are showing on these graphs, so that now what you're trying to do is run your HPC application. But for certain components, use an AI surrogate, which can be super fast. But during some of their retraining, the amount of IO they generate using their own IO, this was with PyTorch, that interferes with the application's IO, and it causes a great slowdown. So having a same way to do IO, in this case, again, Adios, you can greatly speed things up. This is in its infancy, and we show a 20% speed up. But again, that's not bad for something that we just started working with. But again, as you see this convergence of HPC and AI, these are things you got to start paying attention to as we move past the exascale. Okay, and this slide, I'll click again. So the other thing, and someone asked me in the earlier session about this. So imagine here, and this is something that Jay and I did ages ago. In each chunk, so think of each MPI rank, you know all the variable names. So imagine in the metadata, meaning the really small data to describe the large pieces, we'll also generate all these statistics. So given that, again, when I give talks, I like to be in the core part of the room, I would like to perform a query that's in situ. And I just want to be able to know where the temperature is, say, less than 20, because that's probably where I'm going to stand. So we can do that, whether it's through files. And what we'll do is we'll know that for each chunk. Then you can just take from that chunk and then later figure out which pieces. So what's been shown with later publications, when you do this to storage, rather than doing these index technologies, this chunk-based approach actually maps really well to storage as well. So you can get the most efficient queries along the way. So when you rethink of IO and you think about how this happens, so then a new project that now, now I work for Jay. So everyone works for me, yet I work for everyone. So one of our new projects say, but it's not like, we might have about, the wind and the velocity. Well, what maybe, Paul, you want to know is, you want to know where the vorticity is greater than some value, the magnitude. How do we then query that so that instead of saying, well, that's a derived quantity, how do we then query so that we can actually query that without actually introducing extra storage? We have different ways to do that. Some of them are really exciting with the changes in the future. You heard about Mellanox Bluefield. We can do that in the network. You've heard about in Samsung, they're putting processing power. So now imagine that you don't have to move all that data to then compute vorticity in order to figure out where you really want it. Just do that at storage. That will greatly help everyone else. And it will then help the total cost of ownership because you don't have to put as much bandwidth. So this is another thing that we did, which now I have a live experiment. In this case, we work with a fusion reactor. At the time, it's one of the largest. It's in Korea. And now, how do we make it so that that will publish the data? And then we can go directly into, in this case, there was the Cori supercomputer in California, NERSC. And how do we make it so that, again, we're just using Adios, we're subscribing to the data in the memory of the supercomputer, but over in California, even though this is in South Korea. And now we can run some AI algorithm for near real-time effects. And what we showed, and we've had several papers in physics publications, is now we can reduce the data, the time to process from 12 hours to 10 minutes. Now, I know what you're thinking. 10 minutes, it stinks. Because actually, the problem is the thing runs in less than 100 seconds. But this was Intel 5s, and now we're getting it all GPU enabled. So getting another factor of 100 is pretty easy in that case. So that's how we're going to reduce that, because it's not the time in actually moving the data. The movement of the data is very efficient, but it's the processing. So now we're going to GPU enable this. Okay, this is, I'll push again. There it goes. So one of the things now, and one of the keynotes that Eva gave was about workflows. So one of the things in a workflow system is like you're explicitly saying, well, that's producing a file. Move that file here. Now you run. So everyone is placed, but now imagine that we have this componentization. So now it's like everyone is just publishing and subscribing to data. Imagine that's also in where you're monitoring your performance. So now what you can do is you can build in a workflow system, which now doesn't worry about that, but now thinks more about what we call command and control. So what I'm saying is now you start thinking about, well, I can tap in, I can see where there's imbalance. I can say, hey, stop. We don't want you to run. We're going to have something else run. So you can just monitor this in memory, and you can just get that from the metadata. So it's small amounts of data. So you can do this command and control. So we've been developing for the last, I would say, 15 years, a workflow system that basically says, we're going to separate the data management from the workflow. And then we're going to have ways that after the run, we'll use Globus. So we'll have that archived around the world. The performance monitoring, you'll run with TalExec, very lightweight way to run with your applications at scale. And then the performance gets published. We'll have a dashboard, a web interface. So all visualizations are going to produce something, which then the data gets moved to this web interface. So then you can have tens, dozens of users all looking at the visualizations in situ or even after the run. So it's just a way to say we need the separation. Well, one of the things that you find is that you need what we call a schema. Now, normally I would ask people like, do you know what a schema is? But given the time, I'll say, again, a schema is just a well-defined naming system. And if we can get that, we can stop thinking of file format. And now we can start saying, well, we're going to define it this way. We're going to have a standard. We'll have different types of systems that can go and read and write or get input with this. And then we can do this and we can do it in situ. So then in situ viz, you can start thinking about queries in this. You can start thinking about what you want, when you want it, how you want it, and the workflow system controls. And I mentioned performance. And again, what we tried to show, this is running the, this is part of the Fusion Exascale project we had to present recently. And we're trying to say that the performance is so low. It's so tiny, meaning 0.2% of the time that it takes to run, you're having to spend in this. So, I'm sorry, 0.1% of the time. And this is again running. So in the exascale, we talk about these figure of merits. Our charter is we have to be 50 times faster today than when we started, like 7 years ago. We're going to be right now, we see that we're going to be roughly 370. We hope that we can get to 1,000, but it doesn't matter. I'll go with the visualization in my last slide. But now, if you can do this, one of the things that, again, one of the keynotes that Trish gave, she was talking about, again, these, life after exascale. You have to really think about not data, it's information. And how do we then, if you want to say refactor data and prioritize information? So if you go back to your early days of elementary school, like Paul, you remember taking, and learning about PDEs in what, second, third grade. And when you did that, you started learning about like adaptive mesh refinement. Maybe that was high school. And you start learning what you're trying to do and what the insight when you compute is, can you place more computation where you have more physics? Well, can we do that to data? how do we create a mathematical foundation built from, say, multi-grid or adaptive mesh refinement to do this? So then when you think of video streaming, people think of like with fast Fourier transforms, and that's a way to then refactor data into frequency space. Because if you're going to watch a movie, like, you know, if you're going to watch a movie, and maybe it's one of those films that you don't want to talk about, you wanted that quickly stream. You don't have to have every little detail, but if you have the bandwidth and network, you'll get more. Meaning, basically doing that because of you need the time to, you know, to see things. So can we do that with errors? So what we see from this workshop, which I co-led, which was, it's all about the trust, the accuracy, putting error bounds. So we came up, and this was really a mathematician that I've worked with from Brown University. We took a theory of multi-grid. We said, can we refactor the data this way? One of the big things about it, and again, this is the only math that I'll put here, is that it's not just about the data. We mentioned again, Paul, he was interested in vorticity. Well, that obviously involves the curl of the velocity. He needs to make sure that what he's looking at is accurate. So we have to provide mathematical bounds for what we'll call the quantities of interest or the derived quantities. This was a way to mathematically prove, and that's Q of U. So that's Q of U, the primary data, minus Q of U, which is the reduced data. And we can bound it. It's bounded by some norm. We call it an S norm. Think of an L1 or L2 norm. If you don't know, it's okay. But we can mathematically bound that. In this case, it's only for linear quantities of interest. And we need to go further than that. So I'm just going to, this is getting close to the end. I have no idea of my timing. I don't want to know. But what we'll say is, this is a simulation we produce 200 petabytes of data if we wrote everything out. Is that large? No, that's Summit. So some person, they think that's okay. They can, but analyzing 200 petabytes, one of the problems that we don't talk about in high performance computing is most of the data that we save and archive, this is one of the hidden secrets. No one ever looks at. And we build these tape systems. No one looks at. So how do we change that? So here, what we're doing, and again, going back to probably now, you know, when you were undergraduate, you probably learned about probability distribution functions and all the moments that come from that, right? Pretty simple things. In this case, again, think of it as your histogramming. This is in velocity space. We know that physics, right? Classical physics is 6-dimensional, correct? Of course it is, right? We have position, and depending upon Lagrangian or Hamiltonian theory, Jay will tell you it's either momentum or energy, correct, Jay? Yes. Right, that's 6-dimensional. In fusion, we can average out because electrons, we know, basically go in circles. So we can average out. So this is 5D. So we take the 2-dimensional velocity space, and then what we do is we histogram that, and now we can reduce it. In this case, we're using some parts from an autoencoder, going over from seeing where the errors are large from your primary data, looking at your residual, and then we have what we call a QOI satisfaction, or we're doing a post-optimization problem, and then we can reduce the data. In this case, again, the data is quite large, okay? And I'll just explain this a little bit. It's very simple. This, on the upper part, we're just looking at the data from this fusion code, looking at what we call ITER data. That's the large fusion reactor that's being built in Cadarache, France, that's going to be online in 20-something. Yeah, that's right. I mean, do we have Europeans here? It's the biggest, though, international fusion. It's a huge project. And the point is, so here we're just looking on the top at data at one step. And we're trying to reduce the data. And we're looking at, in this case, the errors, the relative errors of the primary data on the upper, your upper left. And what you're seeing is we're trying to bound the error, in this case, a little bit below 10 to the minus 3 for a relative error. So we can bound it. But then we have this post-optimization. So now we can get essentially almost a mathematical proof to say, we can now bound that error to say floating point accuracy, things that you'll see in the middle. So we can take the raw, if I wasn't going to do it, that's the top, where we have errors which are too large. But here we can get compression ratios if we reduce the data to floating point accuracy of over 300x. And that's pretty significant. And then when we actually look at the data as it changes over time, we can then show that we can have the errors bounded. Everything is below 10 to the minus 9. It's not exact mathematical proof. We're working further with this, but it just shows the exciting possibilities of doing that. And again, floating point accuracy. So when you put this together, and again, what you'll see, this was something that we were starting to put up, and we'll put this up for a Gordon Bell nomination next year. You can start thinking about these in situ workflows where I'm coupling codes. I'm coupling visualization that's going to compute and visualize what we'll call, I don't know if there's a way to replay this movie. It's not playing, but it's okay. There's these little things that are coming out over through what we call the X point, which again, going back to your graduate days in school, magnetic reconnection through your X point, it happens on the sun. And what you'll see here is like, all of a sudden, when you can do this in situ viz, and you can deal with all this data, you can make a discovery. And we've never had this discovery before, and it actually matches the experiment. So by having the large scale computing, this can actually show us that we can discover. You need to do all these techniques. It's a workflow if you're going to make discovery. It's not just your application. All right, that was okay. See, so we work with a lot of applications, and I'm almost done. I know I've gone quickly. Okay, so I'm right on with time. So what happened? Okay, whoops. Okay, so what we work with a lot of really large applications, and we've been partnering more with commercial partners like Kitware. And again, they're not trying to make money, but they can lend them, for if you're not on the bleeding edge a lot of times, then they are good partners of ours. And we're making sure the hardware's, the software is really well vetted against all these different applications. And we're working with really large data at the largest scales along the way. So this is, all right. So with that, I'll take questions. Just might as well have questions.
All right, let's thank our speaker here. All right, who'd like to ask something first?
I never get questions. Come on, questions.
Just a comment. I know I've already monopolized you at the conference, so I'll give other people a chance to talk to you. Just a point in that example with K-Star, that's something we should definitely discuss with and highlight with Rob Acker's team. Was that for intershot data, or what was that actually doing?
So we can talk specifics, but right now we can't get into their whole data acquisition system. So we had to do this for proof of principle.
Let's me and you take this offline, and I think that would be a really good topic. This is Sean DeVitt is really interested in exactly that exemplar. Right. He wants us to do his intershot analysis in Cambridge.
And what I'll say is, this is the same technology, like we say, like here, DataMan. And DataMan was actually created from our Australian colleagues for SKA.
Yeah, well, also the SKA.
So this is something where I'm not showing SKA. I could have had an entire presentation on that. But what I'm trying to say is, it's the same technology. And that's the point. Don't reinvent the wheel. And the problem in our community is someone else is going to say, oh, I just want this one thing.
So I think in structural biology, cryo-EM machines, this kind of stuff, we've got some experimental device creating, but, either light sheet microscopy or cryo-EM machines, you've got an experimental source, and I'm wanting to do the analysis somewhere else, again, this could be very useful. We will have a session on this in February.
Well, and one should think about this very quickly in that what I put there is 4 gigabits per second. We didn't reserve the network. This is just running one day. 4 gigabits per second is how many megabytes per second? Is that roughly 500? 500 megabytes per second. The latency by not running off of the same machine in Korea versus going over into California, we added 0.3 seconds or 300 milliseconds. So we're adding a little bit of latency, but then a lot more computing power. So it's like, that's the placement. And those are things you need to be aware. But when the analysis definitely takes well over a few seconds, in this case, 10 minutes, who cares about, 0.3 seconds at that point, if you can have that much more compute? This is where the world's changing. Was there any other questions? Who wants to ask me about reduction? Because I really want to answer on it, but I know we're out of time, right?
So we got one in the back here.
Okay.
And while she's headed over there, the one thing that I would ask is that you mentioned you have a tutorial on this. Can you share that with everybody here, or potentially say next year run a workshop and be able to have people work through that so that they could take advantage of that?
Well, I would call it running a tutorial, not a workshop.
Right. But yes.
I mean, if you're asking me, can we give a tutorial? Absolutely, we can.
Okay. All right.
We did that in Australia. We doing it in Buenos Aires next March. I know it's not exactly here, but again, we do those sorts of things because we really want to grow the collaborators, to grow the software, to make everything better. And we want people at all different scales, because you can't, I want people to understand, when you're from Oak Ridge and people think like, okay, we're the largest, and sure, but the only way you're going to get real software is that you have to have everyone using it. So with that, I'll say thank you.
Okay, I've got one last question in the back here.
Thank you, Scott, for a very informative presentation. With regard to in-situ visualization, how much data reduction can one get when visualizing data in real time?
I'm a little confused by the question, because, I mean, with in situ, you are moving data one way or the other, and then you're taking resources. So if you said getting that visualization, just that picture, an image, then of course one can say you can go from terabytes, tens of terabytes, 100 terabytes, down to a megabyte, but you have a picture, you can't do anything. Imagine now, instead of doing that, that you went from your terabyte down to a gigabyte. You can visualize, but now you can compute all what you want, and you can do that for the rest, of your lifetime if you want. You need both. That's all I'm saying. This reduction principle.
Okay. Thank you.
Philosophy is really gaining traction in the UK and our weather community. So the project that I invited you to come part of, that's a big focus of Brian Lawrence on his weather codes, is how can you get that reduction? And where are you doing that reduction? In the network or at the storage? So this is very apt. This is becoming a big future thing, I believe.
And again, like when you hear about like network and in-network, a lot of it, like when we design an experimental reactor, people always put triggers.
Yeah.
And if you think of the SK and the correlator, what you're trying to do is say, well, there's nothing there. I don't need to store every byte there and move it. I can quickly. So what we call and talk about is pipelines. There's things that you can do in network, and then there's things which get more mathematically advanced. So then it becomes, how do we decompose some of these techniques that we can do part in the beginning and then part later, and then you can just distribute it the way you want. Thanks. I know I got to finish. Thanks, Jay.
All right, thanks. Let's thank our speaker again.